Friedel-Crafts reactions. Now, in Friedel-Crafts reactions, there are two types. One is Friedel-Crafts alkylation, and the other is Friedel-Crafts acylation. Alkylation and acylation are very simple one. In both these, first we start with benzene, and you add for alkylation any RX, say RCl, in the presence of AlCl3. Now you will get a carbocation plus AlCl4 minus. Remember, here the electrophile is carbocation, and since you are getting carbocation, it can be rearranged. That is, it can undergo rearrangement. We have benzene ring, and we have dealt with these in detail in the solved examples. You can have a look at them. And next one is Friedel-Crafts acylation, where you have an acylating agent like RC++OCl, say, and you have a Lewis acid like AlCl3. Now here you are going to get RC++O, a positive charge here, and AlCl4 minus. Now unlike this R+, it cannot undergo rearrangement because the carbon atom here is more stable. As you can see here, this positive charge is stabilized by octet of oxygen, like this one. So here the electrophile is directly this one with no rearrangement. And one more thing which you need to note is that these reactions fails with ring deactivators. That is, if you have, say, NO2, or if you have, say, cyanide, this reaction fails. Now what about this case where you have NH2 plus, say, CH3Cl in the presence of AlCl3? What about this? Just by looking at it, you can say that this is ring activator, and so this reaction occurs. But that is wrong. I'll tell you the reason for it. If you can see, nitrogen has a lone pair of electrons, and this aluminum has vacant orbital. Even instead of Cl, this nitrogen can also donate its lone pair more efficiently than chlorine. And you have the compound like NH2 plus AlCl3 minus. As you can see, nitrogen here is no more plus R, it's only minus I. So it is having a tendency to pull the electrons and no giving of electrons. So it has now become ring deactivator. So Friedel-Crafts reaction won't occur even with these things, where you have pH and H2. Now let us try to look at some interesting chemical properties of this substituted benzene, which is alkyl benzene. Take for example any alkyl benzene with at least one alpha hydrogen. That is, like this one, you can say. Whenever this is subjected to a strong oxidizing agent like, say, KMnO4, you will get carboxylic acid. That is a pH C++OH, irrespective of the number of carbons present in this chain. As an example, I have given here a benzene ring with this one, where you have, this is called as cumin actually. It can be prepared from Friedel-Crafts alkylation, and as you can see here there is a hydrogen attached, so you have got a pH COOH. Whereas for the second case, where you do not have hydrogen here on this carbon, you do not get any product, or you can say that the reactants are remained as such. Now this is the first reaction. You will be studying this in the chapter of carboxylic acids. Now at this point I want to discuss some more reagents, which are SiO2 and MnO2. Now what this SiO2 does is it oxidizes carbon with 2 alpha hydrogens which are adjacent to, say, pH, a single bond, or allylic bond, that is either benzylic or allylic, or even alpha to C double bond O, like this one. I have shown you here. For benzylic it's getting converted to C double bond O is benzaldehyde, whereas for allylic you are getting a double bond O here, that is this compound. And as you can see, for this compound, if you treat it with SiO2, you will get a double bond O here but not here. This is because in the RDS step or in the reaction you are getting an enolate ion. Don't worry about the mechanism now. You are getting an enolate ion whose stability is a favor for us, and as you can see, I am drawing the possible enolate ions. This one is one enolate ion, and from here you will get an enolate ion. The structure is O minus here, and for it you have O minus here. Now this is more stable because it has more hyperconjugations possible. So based on this you are getting this product. Now you need not remember the mechanism for it, just see what it is doing. Now for the second case, if you take where this has only one hydrogen and this has three hydrogens, you are getting a double bond O here, since you have mentioned that it should have 2 alpha hydrogens, and also note that it has only one hydrogen. Now next important reagent is MnO2. What this MnO2 does is it oxidizes benzylic or allylic CHOH to C double bond O. Now this is gonna be very important. Remember that this should have at least one alpha hydrogen. As illustrated in this example, the property should be very clear to you. Here you have a benzene compound, and you have a benzylic OH, and you have a non-benzylic OH, and you have a C double bond C, where you have allylic OH, and here you do not have an allylic OH. This is non-allylic. Now if you treat it with MnO2, this benzylic and this allylic are getting converted to C double bond O, whereas this non-benzylic and this non-allylic are remaining as such. Coming to the final part of theory, here I have given you some of the derivatives of benzene. There is nothing much to explain this. Just have a look at these first, and just pause on your video for a while and see what these are. Right. Here I have given you only a few compounds, but there are many compounds which are concerned with IIT JEE syllabus. Now my sincere advice to you is, whenever you find a compound which is different to you or which you find to be a useful one, just write the compound in a notes, and finally at the end of the second year or at the end of your +2, you'll have a lot of compounds, and just be thorough with them and seek the help of your teacher. And why I am saying all this is, in 1 year, 2-3 years before, a question has been asked based on the common names of the compounds. So it would be better if you know the common names, or at least what are the functional groups present in it. So let us move to the problems regarding this chapter.
Now that we have covered the theory part, let's try solving this very simple question, which involves the ozone layer of the given compound.
The given compound to us is a benzene ring with 2 methyl groups attached to it. Those are in ortho positions.
Okay.
Now this given reaction is simply called reductive ozonolysis, because in the first part you are adding ozone in the presence of non-polar solvent,
Okay.
which is formation of ozonide. I have discussed the structure already and its formation. And second part is addition of a reducing agent, that is the total becomes a reductive ozonolysis.
Okay.
Now in the reductive ozonolysis, what happens is C double bond C gets converted to C double bond O plus O double bond C. Both these are same compounds. Now I've already discussed the mechanism of it, so for this compound we'll just write the products. We have 3 C double bond C's. One is this one is this one, and one is this one. So breaking these bonds and adding double bond O to these carbons, you will get from this part C double bond O and C double bond O, and from this part also we will get the same compound, which is C double bond O double bond O.
Yes.
And from this part you will get double bond O double bond O. Also there will be hydrogens attached to it.
So we'll get 3 dicarbonyl compounds.
Not 3, 2. We will get 3, but 2 of them are same.
Yes.
So whenever this question is given to you, if you write how many different products they are asked, you will write 2. But this is wrong, because
Why, Gopi? Can you explain?
this benzene ring is in resonance.
Okay.
So one more possible structure for it is this one. So
Okay.
if we split this compound,
We'll get different products.
yeah, from this part you will get double bond O, which is same as this one, and from this part you will get C double bond O and double bond O here, and which is same as the previous one. Whereas from this part you will get this one, diketone compound.
Okay.
So if you see the number of different products obtained, they are this one and this one and this one. I'll write down for you. Double bond O, an aldehyde group and a ketone group, and you have double bond O, H here, 2 aldehyde groups, and double bond O, 2 methyl groups here. This is diketone. So the number of different products obtained are 3.
Okay. So one thing you should keep in mind while solving this question is that you have to apply ozonolysis on both of the resonating structures.
Yes. Now we are done with this question. Let's move to the second question of it.
So Gopi, let's start with this question in which this substituted benzene is treated with with these reagents, and you have to find what's X and Y.
Now, the substrate which you are given, this one is called as
Toluene.
toluene. Now this is a very famous reaction. As you are taught in theory, it's called as Friedel-Crafts acylation.
Yes.
Friedel-Crafts acylation, which is addition of RCOCl and in the presence of AlCl3 to benzene. Now let's see what happens here. You know that aluminium has a vacant orbital,
Yes.
and you also know that this AlCl3 is a very good chlorinating agent. That is, it takes this chlorine, lone pair of electrons, and it will give you AlCl4 minus and a stable cation, carbocation it is. I'll tell you how it is stabilized.
It will dechlorinate the acid chloride.
Yeah. This has lone pair of electrons and it will give this to it, and it will fulfill its octet.
So it will be resonance stabilized.
Yeah. Now let's see what happens. You have toluene here and electrophilic aromatic substitution takes place here. This one. And you can see that you have CH3 on the ring, which is ring activating group.
Which is orthopara director.
Yeah. And orthopara director. That is, this can be attacked at ortho position or at para position. But also remember that in the question you are given only one equivalent.
Oh.
So you have to say which of these is most stable one. Suppose it got attacked on ortho position, then you will get an ortho product like this. Like this. And if it get attacked on para position, you will get a product like this.
But which one will be the major product?
Yeah. If you see this, you have CH3 group and this C double bond O ET group. They suffer repulsions
Okay.
than this. So para would be the stable product. So para addition takes place and ortho addition won't take place. But if you have excess here, there is possibility for both ortho and para products. Since you have only one equivalent, only para is formed. So that we are completed with the second question. Let's move on to the third question.
So you should remember that steric hindrance also can determine major and minor products. So Gopi, let's start with this theoretical question in which we have to find the molecules whose dipole moment is 0.
First, let me tell you what dipole moment is.
Okay.
Dipole moment, whenever you have two opposite charges separated by a distance, we said that a dipole moment exists between them and it is given by mu is equal to charge into distance.
Okay.
D is the distance between these atoms. Now, if you take any covalent molecule where X and Y are
Yes.
not of same atoms, then there always exists electronegativity difference between them. Suppose that Y is more electronegative than X, then
So it will pull electron toward itself.
yes, as a result of it, Y develops a partial negative charge and X develops a partial positive charge. So we have two charges separated by a distance. As a result of it, there exists a dipole moment in this molecule. Now,
But Gopi, by looking at these figures, it seems that 3 of them will have 0 dipole moment as they are symmetric.
yes, it appears to be that they have zero dipole moment, but that's not the case.
Can you explain why?
Yeah. Of course, it's true for first compound. I'll tell you that. If you take first compound, where you have benzene ring and two cyanide groups attached at para positions,
Okay.
as shown here. Now, as you see here, this carbon and this nitrogen both are sp hybridized.
Yes.
That is, they have linear structure. So you can observe that this lone pair and this lone pair cancels each other. That is, their dipole moment cancels each other.
The compound is perfectly symmetric.
Yes, and dipole moment due to this asymmetric bond, which is nitrogen and carbon bond, cancels each other, and due to this one, which is a triple bonded carbon and a double bonded carbon, here also the same thing, both cancels each other and we get net dipole moment as 0. Now let's move to the second part of it, where you have two OH groups instead of two cyanide groups. Now, unlike cyanide groups, oxygen atom here is sp3 hybridized. Now if you look into the question, they have asked you the dipole moment is 0 always, but this is not the case with oxygen, because I have already told you that it is sp3 hybridized and this bond can be rotated in many angles as possible.
Yes.
Like this. So we cannot be sure that this lone pair and this lone pair dipole moments cancel, and this hydrogen and this hydrogen dipole moment cancel. And this figure clearly shows that supposing these hydrogens are in the plane of benzene, if they are aligned like this, they have a resultant dipole moment in this direction, and if you take these two dipole moments because of hydrogens, they are in this direction. But the dipole moment due to this carbon and this oxygen and this carbon and this oxygen cancels.
So the dipole moment will be different for different conformers.
Yes. So this dipole moment is not 0 always. But there is one conformation where the dipole moment can be 0, and that is when OH, when this H and this H are opposite in opposite direction. That is, if you take this benzene plane and if this OH bond shows dipole moment in this direction and this one in this direction,
They will cancel.
they will cancel away. And only in one conformation we have dipole moment 0.
Okay.
So for the given question, answer would be only 1. And the same is the case with SH, because oxygen,
OH and SH are similar.
because they are of same group and they have same hybridization, which is sp3. Now that we are done with third question, let's move on to fourth question in benzene chapter.